Today is the day. Today we finally define probability. Recall the basic setting in which all of the probability study takes place. Consider an experiment, such as flipping 2 coins. It may result in one or more outcomes. The set of all outcomes is called the sample space. For instance, if you flip 2 coins, the set of all outcomes is this. A subset of the sample space is called an event. For instance, in this case, the event could be getting the head once, in which case the event consists of 2 outcomes, HT and TH. If the outcome of our experiment falls into E, then we say that the event E occurs. Today we define probability. Probability will be a number assigned to each event E. It will basically gauge how likely the event E is. Some events are not likely at all and will receive probability 0. Other events are surely likely and will receive probability 1. And there will be some middle ground. For instance, this event, as we will see, has probability 1/2. So again, the probability is an assignment of a number to an event. Not all assignments are allowed. There are certain rules. So we'll define probability now axiomatically. We will lay down these rules that we may call axioms that such an assignment must always satisfy. So a probability is an assignment of a number. Let's call this number P of E to an event. The assignment which satisfies the following properties that we may call axioms of probability. First, the probability must always be non-negative for any event E. Second, the probability of the entire sample space. Let's think, what should it be? The entire sample space contains all possible outcomes, anything that can happen. For instance, any combination of flips. What is the probability that something happens, anything happens? It's 1, always 1. So probability that something happens at all is 1. And the third axiom is the most complicated one. It says the following, that if you have an event E, and E can be decomposed into a union of disjoint or mutually exclusive events. Remember, mutually exclusive means that they don't have an overlap. So if E can be decomposed like this, then the probability of E can be computed by summing the probabilities of each part. So for any mutually exclusive events, E1, E2, etc., En, where n can be finite or infinite, the probability of their union equals the sum of the probabilities. This axiom is called the additivity axiom because it allows to compute the probability of more complicated events by adding the probabilities of the simple events, their constituents. This is the rigorous definition of probability. a couple of remarks. First, as we mentioned, the number of events, the number of little constituents, can be finite or infinite. In case it is infinite, this sum is the sum of infinitely many terms. Such sums, as you may remember from calculus, are called series. And the series on the right-hand side, this one, is required to converge as part of this definition. One more remark. These axioms of probability may sound a little artificial, but in fact, there are many things in nature, in our lives, that satisfy these axioms. For instance, the notion of length, the notion of area, satisfies axioms 1 and 2. Indeed, the area of any set on the plane is non-negative, and as this picture shows, the area of any set can be broken down into a sum of the areas of its parts. Similarly, the volume satisfies axioms 1 and 2. In physics, mass satisfies that. If you break down an object in 2 or more parts, the mass of the object can be computed from summing up these parts. The notion of percentage satisfies all 3 axioms. If you normalize the percentage to be 1 instead of 100, the percentage is always non-negative. It's the total percentage is 1 or 100%, and it is also additive. But how can we compute probabilities of various events? How do we know this assignment P in practice? The simplest kind of probability is called uniform probability, and it may happen in practical problems. The uniform probability makes everything equally likely. All outcomes have the same probability. More formally, suppose there are finitely many outcomes, and that means that the sample space is a finite set. And let's assume that all outcomes are equally likely. This simply means that probability of any outcome, let's call it little s, and the curve braces mean that we look at this outcome as an event, has the same probability of any other outcome. If this happens, then we call such probability the uniform probability. We will give specific examples in a short while. But for now, let's observe that in this case, we can compute the probability of events very simply using this formula. For any event E, the probability of E is just the ratio of the number of outcomes in E to the total number of outcomes in S. Let's give a formal proof to this. Let's list all outcomes and call them S1, S2, and so on. And let's suppose there are capital N of them. Look at these events. Each event will consist of a single outcome. The Venn diagram looks like this. There are 1, 2, 3, 4, 5, 6 outcomes here, for example. The sample space can be expressed as the union of these events. This is our total sample space S, and it is the union of these events. Therefore, by the additivity axiom, the probability of S is the sum of the probabilities of its parts. But we know from axiom 2 that the probability of S is 1. Probability of anything happens. That's always 1. And we assume that the probabilities of these events are the same. All outcomes by our assumption are equally likely, and these are their probabilities. All these numbers are the same. So what do we get? The sum of n terms, all of them are the same, and the sum equals 1. Well, that means that each term has value 1 over n. So we just showed that in uniform probability, the probability of every outcome is 1 over n. And then you sum them up. If the event E consists of only some outcomes, let's say S1 through S little n, then similarly, E can be written as the union of only some of the EIs. And here in the picture, maybe this is our event E. Then again, by additivity, the probability of E is the sum of the probabilities of these mutually exclusive events P of EI. There are little n terms here, and each of these terms, as we know, equals 1 over capital N. So the sum is little n over capital N, which is the same as the size of E over the size of S. And this proposition is proved. If you find it too abstract, think about this specific situation, where E consists of 3 outcomes, and there are 6 outcomes total. What is then the probability of E? The probability of E will be 3 over 6, which is 1/2. And now, 2 specific examples. Let's flip 2 coins, in which case there are 4 outcomes making this sample space. We can assume that all these outcomes, all 4, are equally likely. Why? Because the coin doesn't know what side it will come up. And so all possible combinations have the same probability. Then let's compute the probability of getting 1 head in a flip of 2 coins. By this formula, it is the probability of the number of outcomes in E over the number of outcomes in S. E consists of 2 outcomes, HT and TH, and so it's 2 over 4. So the answer is 1/2. The probability that in 2 coin flips you get 1 head is 1/2. Another example. Here, experiment is to choose 10 rats from a lab that has 100 rats, of which 40 are sick and 60 are healthy. We considered this example before, and now we cover it more vigorously. The sample space consists of all possible selections of 10 rats, all subsets that we can choose from 100. We can assume that any choice of 10 rats is equally likely. We don't look. Any subset of 10 rats can be as likely as any other. So all outcomes are equally likely. And let's compute the probability that we select a representative sample of rats. One that has 4 sick and 6 healthy. The probability of E then is this ratio. Let's look at the denominator first. How many ways are there to choose 10 rats from 100? That's 100 to choose 10. And then let's look at the numerator. How many ways are there to select 4 sick from 40 sick? and 6 healthy from 60 healthy. That's 40 choose 4, 60 choose 6, and then we multiply by the multiplication principle. And when we compute, the answer is 0.26. That is the probability to select a representative sample. The uniform probability, one in which all outcomes are equally likely, is very helpful in computations, but it doesn't always happen in practice. For instance, if you rent a movie on Netflix, not all outcomes are equally likely. You will prefer some movies over others. In addition to uniform probability, there are many other probabilities. We will study some of them. Stay with me. Have fun.